Every single day, more than 100,000 tons of glass emerge from furnaces across the world. In Brazil alone, production reaches an astonishing 1.5 million tons each year. To satisfy this massive demand, thousands of tons of sand are processed daily. But have you ever paused to wonder, how can something as soft and weightless as sand be reborn into one of the strongest, most versatile materials on Earth? Today, we'll journey through that transformation, from grains of silica to shimmering sheets of glass. Stay with me until the end. The modern world simply couldn't exist without it. This silent marvel of engineering surrounds us, towering in skyscrapers, protecting us in automobiles, lighting our homes, and giving clarity to our screens. Though it may appear fragile, this material is anything but. When reinforced, it endures blazing heat, crushing pressure, and even violent impacts. Its remarkable resilience has earned it a place as one of the most indispensable elements in construction and technology alike. The origins of glass stretch back thousands of years. Legend says it was discovered by accident when ancient people, experimenting with fire, mixed silica-rich sand with wood ash containing sodium carbonate. As the mixture cooled, it hardened into a mysterious, translucent substance unlike anything they had seen before. In ancient Egypt and Mesopotamia, around 3,000 years before Christ, artisans crafted beads, amulets, and vessels, small, colorful, and opaque treasures born from fire. Centuries later, the Romans changed everything. Around 50 BC, they invented glassblowing, revolutionizing production and allowing delicate, intricate forms to be shaped in moments. During the Industrial Revolution, the art evolved again. Machines and modern furnaces enabled glass to be produced in mass quantities. Flat glass appeared for windows and mirrors, but perfection still came at a price. The process was slow, costly, and far from flawless. Each sheet required grinding and polishing before it could shine. Then came a breakthrough that reshaped the industry forever. In 1952, British engineer Sir Alistair Pilkington introduced a revolutionary process known as float glass. By letting molten glass glide over a bath of liquid tin, he achieved something extraordinary: a perfectly flat, seamless surface. For the first time, glass could be produced continuously, at scale, and with stunning precision. The era of smooth, crystal-clear glass had begun. The ingredients are deceptively simple: silica sand, sodium carbonate, and limestone. To these, manufacturers add fragments of recycled glass called cullet to save energy and reduce waste. This dry blend, known as the batch, starts its journey deep in nature. Silica sand, rich in quartz, is mined from riverbeds, dunes, and sedimentary rocks. Once extracted, it's carefully washed, screened, and purified until every grain gleams. From the mines, the refined sand and other raw materials travel to vast glass factories. The largest of these receive up to 5,000 tons of silica each week. Inside towering silos, the ingredients wait, ready to be drawn into the production line. Every element is measured with precision and blended to perfection. For in this process, each component plays a vital role. Silica makes up about 60% of the recipe. Mixed with sodium carbonate and limestone, its very structure begins to change. These minerals act like chemical keys, lowering the sand's melting point and allowing it to fuse more easily. Calcium carbonate helps this transformation, while limestone strengthens the final result, ensuring the glass can endure both time and pressure. Recycled cullet joins the mix, melting faster than virgin materials and saving immense amounts of energy. It's sustainability in motion, reducing environmental impact while improving furnace efficiency. Small additions of iron oxide and cobalt tint certain varieties with a subtle blue glow, giving each paint its unique character. The prepared batch is fed into a colossal melting furnace, an inferno built from refractory bricks that never sleeps. Operating around the clock year after year, it can run continuously for up to 15 years. As the mixture enters one end, heat rises to over 1,500 degrees Celsius and the transformation begins. Natural gas fuels the blaze. Inside, the raw materials dissolve and fuse, releasing gases and forming a molten, glowing mass. The liquid then passes through an even hotter zone, where bubbles and impurities vanish. The constant motion within this fiery sea keeps the mixture uniform, perfectly balanced in texture and clarity. Now at over 1,100 degrees Celsius, the molten flow glides onto a bath of liquid tin. Within a chamber protected by nitrogen and hydrogen, the tin remains unoxidized. Because the glass is lighter, it floats effortlessly on the metal, like oil drifting atop water. Gravity and surface tension spread it thin and flawless, shaping a continuous ribbon of smooth, flawless glass. The final thickness depends on how quickly it moves forward and how the edge rollers guide its path. The tin beneath ensures a mirror-like finish, flat, gleaming, and pure. Emerging from the tin bath, the glass is solid but still glowing with heat. It travels into a long annealing tunnel known as the lair. There, it cools slowly and evenly, relieving internal stress. Entering at about 600 degrees Celsius, it exits on the other side cool to the touch, strong, stable, and ready for the next phase. Conveyors carry the cooled sheets to automated cutting stations. Diamond-tipped blades score the surface, tracing lines with surgical precision before the sheets snap neatly along the marks. Each piece can be trimmed to standard dimensions or tailored to custom sizes, depending on its final purpose. In the control room, a team of technicians oversees everything: temperatures, line speed, and glass quality, all monitored in real time through glowing screens. It's a ballet of machines and minds working together to ensure every sheet meets the highest standards of safety and clarity. Airfit glass doesn't go to waste. It's crushed, recycled, and reborn, fed back into the process as cullet for the next production cycle. The flawless sheets are lifted, stacked upright on sturdy metal racks, separated by protective layers, and prepared for shipment to customers around the world. Yet not all glass is made by machines. In artisanal workshops, the ancient methods still live on. Here, every step is guided by hand and instinct. Each furnace chamber holds molten glass of different hues, destined to become vivid, handcrafted plates. When the molten mass is ready, artisans move quickly, scooping it out with long-handled ladles and bringing it to the mixing table before it cools. To create marble designs, up to 5 distinct colors may be swirled together in mesmerizing patterns. Before stretching the material into sheets, the craftsman uses a special iron fork to stir the glowing mixture, blending colors like a painter working with fire. The molten body is then fed into roller machines, which press and flatten it evenly as it flows between them. The distance between the rollers determines the final thickness, thin as light or thick as armor. Once formed, the sheets move into the annealing furnace to cool slowly, preventing cracks or breaks during cutting. Here, even the slicing is done by hand, with tools tipped in diamond or tungsten carbide, a delicate balance between precision and artistry. And so, every day, more than 100,000 tons of glass are created across the planet, a symphony of fire, metal, and human ingenuity. Well, if you'd like to discover how a Bic pen is made, check the link in the description or the first comment. If this journey fascinated you, leave a like and share it with your friends. Tell us where you're watching from and what you thought of this episode. Every airplane tire begins as a masterpiece of precision engineering. They are the only point of contact between a machine that defies gravity and the ground that welcomes it back. During every takeoff and landing, they endure immense pressure and punishing speed. But have you ever stopped to imagine how these giants of rubber come to life? Today, we're stepping inside specialized factories where science and craftsmanship intertwine. Together, we'll follow the entire creation process, discovering what materials are used and how these incredible structures manage to hold tons of weight without a single explosion. Stay until the end. Aircraft tires are built to survive the impossible. Each one must absorb violent impacts at tremendous speeds while carrying astonishing loads, all while remaining lightweight and compact. They operate in some of the harshest environments known to engineering, where temperature and pressure shift faster than the eye can blink. The process begins with a material stronger than ordinary rubber, a aramid. This synthetic fiber is the same found in bulletproof vests, fiercely resistant to heat and wear. To put it in perspective, standard rubber begins to melt at around 260 degrees Celsius, while aramid remains solid beyond 500. That strength grants each tire the endurance to complete up to 500 flights before replacement. It's the unseen armor that keeps every landing safe. From there, construction begins with the heart of the tire, its inner layers. Multiple sheets of reinforced fabric, soaked in special rubber compounds, are precisely overlaid and molded into a perfect cylinder. These layers form the backbone of the structure, giving it the mechanical strength to carry entire aircraft, cushion violent landings, and remain stable under unimaginable pressure. Though complex in design, the composition is elegantly simple: rubber, synthetic fabric, and a touch of steel. The steel, just 5% of the total, forms what's known as the steel belt, braided cords encased in rubber that tie the whole system together. Between these fabric layers, steel belts are carefully inserted, adding stiffness and stability. They help prevent deformation as the tire spins at breathtaking speeds and strikes the runway with brutal force. Together, they form a structure that is both flexible and indestructible. Each one is built to withstand speeds exceeding 400 kilometers per hour and support aircraft weighing between 22 and 33 tons. Whether resting on the runway or racing through it, it's not just a tire, it's a precision instrument of survival. Once the internal carcass is formed, attention turns to the outer shell. The surface is carefully treated and pressed, preparing it to receive the tread, the layer that meets the Earth itself. The tread is a work of art in itself. It's the layer that must grip the ground, endure tremendous friction, and resist both heat and wear without ever losing traction. Composed of high-resistance rubber, it's applied as continuous strips or sheets, wrapped seamlessly around the carcass. Once bonded, the entire structure is pressed and cured until every molecule fuses into one cohesive body. Unlike car tires, airplane treads have fewer and shallower grooves. Their purpose isn't aesthetic, it's to combat hydroplaning during landing. Each groove is sculpted with precision during vulcanization, using molds designed to the micrometer. The assembled tire then enters the vulcanization mold, where chemistry meets heat and pressure. Under these intense conditions, raw rubber reacts with sulfur, undergoing a transformation known as vulcanization. The result is elasticity, durability, and permanent adhesion between tread and carcass. Here, the tire acquires its final form, its strength, and its signature pattern, ready to face extremes few materials could endure. When the heat subsides, a new phase begins. Testing. Every tire is subjected to meticulous inspection and rigorous trials. Specialists examine the surface, measure pressure tolerance, and test for balance, acceleration, and compression. Every tire must prove itself worthy before it ever touches a runway. Then come the landing simulations. To mimic the brutal reality of takeoff and touchdown, engineers use specialized trucks that accelerate to precise speeds before pressing the tire against a concrete or asphalt track with hydraulic force. The impact replicates what happens every time an aircraft returns from the sky: violent, fast, and unforgiving. Here, on wet runways, an Airbus A350 performs landing tests under sheets of water. These experiments push tires and brakes to their limits, ensuring reliable performance even in the worst weather. Each droplet, each spin confirms one critical truth: that an airplane can stop safely even in heavy rain. It's a symphony of precision, ensuring that the tire, brake, and landing systems meet the strictest aviation standards on Earth. Another essential trial is the fatigue cycle test. Landing gears are subjected to thousands of repeated load and release cycles, simulating years of takeoffs and landings in just a few hours. These relentless tests expose every weakness and prove whether the gear can endure decades of flight. While they might appear similar at first glance, airplane and car tires are worlds apart. Their internal structures, materials, and functions differ dramatically. Take pressure, for example. A car tire is filled to around 32 pounds per square inch, but an aircraft tire begins at 200. That's enough strength to carry up to 38 tons of weight. And unlike cars, planes rely on nitrogen, an inert gas that hardly expands with heat, to keep pressure constant even at extreme altitudes and temperatures. And so, thousands of aircraft tires are crafted every year across the globe. Each one is a quiet guardian, built to face incredible forces, ensuring that every takeoff and landing happens with perfect precision. If this journey fascinated you, don't forget to leave a like and share it with your friends. Tell us where you're watching from and what you thought of today's episode. Subscribe to the channel and ring the bell to catch every new adventure in engineering. Thank you for staying until the end. Keep exploring, and may your path, like these tires, always stay steady and strong. Each of these uranium fuel cells produces enough heat to generate 1 million kilowatt hours of electricity, enough to power thousands of homes for an entire year. But have you ever wondered how enriched uranium is obtained, and how something so small can hold so much power? In today's video, we visit the world's largest high-grade uranium deposit and a nuclear fuel factory to discover how uranium is extracted from nature and how one of the planet's most dangerous metals is processed. Stay with me until the end. Please leave your like, subscribe, and turn on the bell for all notifications. The history of enriched uranium is tied to the birth of nuclear energy. Uranium was identified as a chemical element in 1789 by the German Martin Heinrich Klaproth, but no one yet knew its energy potential. In 1896, French physicist Henri Becquerel discovered radioactivity when he observed that uranium emitted rays spontaneously, a discovery that inspired Marie and Pierre Curie to identify elements such as radium and polonium. In 1932, James Chadwick discovered the neutron, a particle essential for nuclear fission. In 1938, German scientists Otto Hahn and Fritz Strassmann discovered that uranium-235, a rare isotope of natural uranium, could undergo nuclear fission. They demonstrated that a uranium atom could be split when struck by neutrons, releasing a huge amount of energy. Natural uranium contains 99.3% uranium-238, which does not undergo immediate fission, and 0.7% uranium-235, which is ideal for fission. Increasing the proportion of uranium-235, a process called enrichment, was essential for both reactors and nuclear weapons. During World War II, the United States led the Manhattan Project. Scientists like Enrico Fermi and Robert Oppenheimer developed uranium enrichment techniques using processes such as gaseous diffusion and centrifuges. These machines, spinning at extremely high speeds, separated isotopes by weight, making enrichment more efficient. The result was the atomic bomb Little Boy, dropped on Hiroshima in 1945, which used enriched uranium-235. After World War II, many countries began investing in the civilian use of enriched uranium for nuclear reactors that generate electricity. For power plants to operate, uranium must be enriched to between 3 and 5% uranium-235. For bombs, however, enrichment levels exceed 90%, which is why there is so much concern about nuclear proliferation. Today, enriched uranium fuels reactors that generate about 10% of the world's electricity. The process begins at uranium mines located in remote regions. Countries such as Australia, Kazakhstan, and Canada together account for more than 60% of the world's uranium production. Uranium is found mainly in the mineral uranite, also known as pitchblende, usually in low concentrations ranging from 0.1% to 2%. In the Canadian province of Saskatchewan lies the world's largest high-grade uranium mine. Here, ore can exceed 20% uranium concentration, up to 100 times higher than in typical mines. The extracted uranium is used mainly as fuel for nuclear reactors to generate electricity. The uranium ore lies beneath a thick layer of water-saturated sandstone, meaning that all the rock's pores are filled with groundwater. To reach the ore without flooding the mine, they use techniques such as artificial ground freezing. Workers use tungsten carbide drills aligned like rows of teeth to bore through the rock. These first holes allow the installation of pipes that remove heat, turning the water in the sandstone pores into ice. This creates a frozen barrier that prevents water from entering and makes it possible to reach the uranium ore safely. The miner operates the equipment remotely, adding a new section of pipe to the end of the drill every 5 feet to penetrate 430 feet into the sandstone bed. Installing just one section of pipe can take up to 8 days, and there are 200 of them. A freezing plant above ground chills calcium chloride brine to -30 degrees Celsius and distributes it through the freezing pipes. The brine absorbs heat as it freezes the soil and then returns to be cooled again. Ore extraction begins above the uranium deposits. They use this drill to bore into the ore body and make an initial small diameter hole known as a pilot hole. The pilot hole traces the drill's path to the ore and creates an entry point for larger mining equipment. From an elevated position, the drill bores vertically through the rock to reach a specific level below the ore body. They are now ready for the reaming drill. This reamer is raised through the pilot hole, widening the rock as it's pulled upward, and the fragmented ore falls into what's known as the extraction chamber. A remote control system keeps miners at a safe distance from rockfall hazards and also minimizes their exposure to radioactive uranium. As an added precaution, the mine is continuously ventilated with fresh air every 20 minutes. Controlling the operation from afar, the operator drives the load to a scanner that measures the ore's radioactivity. The scanner determines that the uranium content is around 15 to 18%, considered extremely high quality. The vehicle then dumps the ore into a chute. From a control room, an operator uses a hydraulic hammer to crush the ore into pieces. The crushed ore is then sent to a mill that grinds it into fine sand. Water is added, turning the sand into a slurry that is pumped to the surface. Trucks transport the uranium-bearing mixture to a mill 80 kilometers away. They stop at a special unloading facility where a vacuum system aligns with the tank. Once positioned, a vacuum tube enters the tank and sucks out the slurry. After washing and a radiation check, the truck leaves the facility. The powdered ore is treated with acid to extract uranium. The mixture is placed in large acid-filled tanks, where the acid dissolves the uranium but not the rest of the rock. The rock settles to the bottom, while the uranium-rich acidic solution flows onward, leaving unwanted minerals behind. Using a series of chemical reactions, they further purify the uranium, then heat it to 850 degrees Celsius. First, the uranium is converted into a gas to enrich uranium-235, the isotope needed to create a chain reaction. This gas is fed into centrifuge machines where centrifugal forces separate the uranium isotopes by mass. Uranium-235, being slightly lighter than uranium-238, becomes more concentrated near the center of the centrifuge, allowing it to be separated. Once separated, it becomes concentrated into a black coal-like powder. This uranium powder flows into 55-gallon steel drums. The drums are sealed and labeled to indicate their radioactivity. The drums are then shipped to a nuclear fuel processing plant. The uranium changes from black to yellow as it's converted into uranium trioxide, an intermediate chemical form in the processing chain. The uranium trioxide is sent into specially designed inverted cones. On arrival at the facility, a valve opens at the bottom and the powder flows into conveyor tubes that carry it into the plant. Inside, the uranium trioxide powder is dissolved in acid. A worker collects a sample to test density and chemistry, confirming that both are acceptable. Next, they add a reagent to convert the dissolved uranium back into a solid. After additional processing, the uranium trioxide is converted into uranium dioxide, the chemical form required for nuclear fuel. Centrifuging the uranium dioxide mixes particles of different sizes to create a more uniform blend. Chemical processing also changes the uranium's color, turning it into a fine black powder. Using several tons of pressure, presses mold the uranium dioxide into pellets. A rotating wheel with protrusions guides the pellets toward a conveyor chute. A uranium pellet the size of a peanut generates the same amount of energy as 1,800 pounds of coal or 1,200 pounds of oil. A conveyor carries the pellets to a furnace where, over 24 hours, heat removes their pores. During this process, the pellets shrink, increasing the uranium's density. Here's a before and after image of the shrinkage. A robotic arm loads the pellets into a tray and levels them, while the conveyor moves the tray forward. Another robot places zirconium fuel tubes into a rack. Zirconium is a metal highly resistant to heat and corrosion, yet neutrons can freely pass through it during fission. The tube rack meets the pellet tray, and a robotic loader pushes a stack of 30 pellets into each tube. The tubes pass through an automated welder that seals their ends. The next robot retrieves the completed uranium fuel rod and transfers it to an assembly fixture that arranges a total of 37 rods vertically within the device. After the assembly is closed at both ends, a robotic arm transfers it to a scale. This weighing confirms that the correct amount of uranium is present in the bundle before it's burned in a reactor. The amount of radioactivity emitted by the nuclear fuel bundles is very low, making them safe to handle while workers prepare them for transport. Each of these nuclear fuel cells contains enough uranium to power thousands of homes for a year. The fuel is received at the nuclear plant, where it will be inserted into the reactor core. In nuclear reactors, uranium serves as the initial energy source that eventually becomes electricity. Each uranium filament produces enough heat to generate 1 million kilowatt hours of electricity. To come to life, they must be placed into the reactor core. The reactor's 480 tubes can each hold up to a dozen fuel rods, and when 5,760 rods are in place, the show begins. Nuclear fission converts matter into energy, which is released as tremendous amounts of heat. Some uranium atoms inside these fuel rods are excitable, and when excited, they begin releasing neutrons in all directions. These tiny neutrons can pass through the zirconium walls of the fuel rods, flying from one tube to another until they collide with another uranium atom. When that happens, the atom splits, releasing energy and more neutrons, and so a nuclear chain reaction occurs. But when it accelerates too much, it must be stopped, or else the reactor won't function as intended. The reactor is not only sealed within 2-meter-thick reinforced concrete walls, but also shuts down automatically if temperature rises or pressure drops too quickly. The heat is used to convert water into steam, a carefully controlled process. In the plant's control room, enormous turbines housed in a hall 1,300 feet long and 20 stories tall convert steam into electricity. The turbine spins at 1,800 revolutions per minute and drives a generator. The generator's massive rotor converts motion into more than 750 megawatts of electricity, enough to meet the needs of 500,000 people. After about a year in the core, the fuel rods are depleted but become extremely hot and radioactive. They're so hot that they must be stored underwater for 10 years before they can be safely disposed of. The rods are placed in a pool at the plant to cool their temperature and dissipate radioactivity. Submerged in this 26-foot deep pool are more than 700,000 radioactive fuel rods.